Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Qayyum bin Muhammad Jani and my number ID is TJ23050.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Adila Nasuha binti Abu Bakar and my matric number is TJ23048.
My name is Nuralisha Aisyah binti Ahmad and my ID number is TJ23052.
Assalamualaikum. My name is Aimi Fazlin Akilah binti Muhammad Kirudin, TJ23051.
Tablet compressor model. This simple setup uses the basic principles of fluid mechanics, which is the study of how fluids move and behave. We're applying Pascal's law, which says that pressure in a confined fluid is transmitted equally in all directions. By using hydraulics, we can transfer force through water-filled syringes to press powdered material into a tablet, but in this case, we're using clay dough instead. Hydraulics are perfect for this because they provide smooth, consistent pressure, which is essential for forming tablets that are uniform and don't crack. What's cool is that our model also ties into sustainability, which it uses reusable materials like syringes and water, with no electricity and very little waste, following the reduce, reuse, recycle principle. And in the real world, this process is crucial in the pharmaceutical industry, where tablet compression ensures every dose is safe, effective, and easy to use.
The material that we use is L-shaped wooden board, spring, pipe, eraser, small string, large string, metal root, tube, and glue. At first, we choose a L-shaped wooden board as the base platform for our model. Next, we glue a spring on the base to serve as a key component in the pressure mechanism. Then, we insert a cut eraser into a pipe and attach it onto the spring using the glue to ensure the stability. We also glue a small string and extend the string holder using a metal root to allow for more flexible movement. On the right side of the small string, we attach a large string which functions to generate greater hydraulic pressure. Finally, both strings are connected using a tube to ensure a smooth pressure flow between them. An addition and improvement, we glue an extra pipe at the small string to act as a guide and stabilizer for the metal root to prevent it from tilting while compressing the tablet.
When the large string plunger is pressed, pressure builds up inside it. This pressure is transferred through the fluid in the tube to the small string. The small string's piston is pushed downward, acting as a puncher on the plasticine. Depending on the fluid types, air versus water, pressure transmission will vary. Water, incompressible, transmits pressure efficiently. Air, compressible, absorbs some pressure, reducing effectiveness. The amount of compression on the plasticine depends on the size of plasticine, the fluid used, and the force applied via the large string. Small plasticine plus water shows successfully compressed. Why? Water is incompressible, so when the large string is pressed, the pressure is transferred almost entirely to the small strings. The water tablet requires relatively low force, so the pressure from the large strings is sufficient. The compression was smooth and efficient, indicating effective force transmission. This shows how hydraulic system can multiply force effectively when the load is within system capacity. For large plasticine and water, shows fails to compress fully. Why? While water still transmits pressure efficiently, The force required to compress a larger volume of plasticine exceeds the pressure limits of the small syringe. The small syringe has a smaller piston area, and although pressure is high, the mechanical output force is not enough to larger object. This reflects a limitation in mechanical advantage. The load was too resistant or large for the system pressure range. For small plasticine and air, shows partial compression. Why? Air is compressible, so when the pressure is applied to the large syringe, some energy is used to compress the air rather than transmit it. This results in a delayed and weaker response in the small syringe. The small tablet is still soft enough to yield slightly under the reduced force, but compression is incomplete and less effective. This demonstrates that hydraulic systems use liquids instead of gases when consistent force transmission is needed. Large plasticine and air shows fails to compress. Why? Air's compressibility causes significant loss of force transmission. Combined with the high resistance of the large plasticine, the small syringe lacks sufficient pressure and mechanical advantage. The result in a total failure in compression, showing that gaseous medium are ineffective for high force application in small-scale hydraulic system. It highlights the need for system optimization in load handling.
The tablet press model created for this project highlights the real-world application of fluid mechanics, especially in how pressure is used in mechanical systems. By using a syringe, metal rod, and wood, this simple setup stimulates how hydraulic pressure can compress material, just like in the pharmaceutical tablet production. This kind of model is particularly useful in educational environments. It visually demonstrates Pascal's law, where pressure applied to a fluid is transmitted equally in all directions. That principle is key in many systems, from car brakes to industrial machine. Besides being a learning tool, the model also serves as a basic prototype of actual tablet press machine used in pharmaceutical industries. It shows how powder is turned into tablets using controlled pressure, all without expensive equipment. The project was successful in applying fluid mechanics to build a working, low-cost model of a compression system. It gave a clear view of how hydraulic pressure works and how it can be used to do a real mechanical work. See, in this case, is the pressing tablets. Throughout the testing process, the model performed well, consistently compressing material using fluid force. This confirmed the basic operation of hydraulic systems and reinforced the connection between the theory and the real-world application. However, a few improvements are recommended. First, sealing the shrink system better would help maintain consistent pressure. A pressure gauge could also be added to measure how much force is being applied. That would make the model more precise and informative. And then also it can be replacing the wooden parts with metal or durable plastic, and it could make the structure more stable. And then adding a mold to shape the tablets more evenly would make the result more consistent. And for a more advanced version, a small motor could even be added to automate the pressing action. In conclusion, the tablet press model is simple yet powerful way to understand fluid mechanics in action. With a few upgrades, it can become an even better tool for learning and experimentation in engineering and pharmaceutical studies. So that's all. Thank you.